Right. Good evening, everyone, and welcome to our CAWASA Wednesday webinar. This evening, we are pleased to have Mr. Jon Grant as our guest speaker. And I would like to thank Valerie as well for joining with us as our main sponsor, that is Operators Without Borders, in finding us some very good subject matter experts. So without further ado, I will ask Mr. Jon Grant to introduce himself and the topic, and he can proceed with the webinar this evening.
Sure thing. Thank you very much for having me, Ignatius, and and Valerie as well. And yeah, I've got my colleague Iker with me as well. He can wave. He's got moving backgrounds. That's always very cool. So yeah, a bit about my background. So I've been at Sentry for about 4.5 years. And I'll tell you a bit about the background technology in terms of monitoring. Before that, I was with an AI company that optimized water and wastewater treatment. And before that, I was at a water technology accelerator. So I've been in water wastewater for about 12 or 13 years, based up in Toronto. It is freezing cold and raining right now. So I'm wishing I was where you guys are all based. And yeah, really excited to be here. So now I will do the number one question for every presentation now. Can everyone see my screen?
Yes.
Yes, we are. Yeah.
Perfect. And I guess this group is kind of small enough where if you have any questions, feel free to ask them or pop them up in the chat. I should be able to see the chats pop up. But yeah, let's love to keep it casual and friendly. So what we're going to talk about today is reliable real-time monitoring. That's generally a challenge in pretty much every wastewater setting that I've come across. So we'll talk a bit about that. And the technology I'm talking about, it was first developed by Dr. Patrick Kiley. He's the CEO and founder of our company, based on his postdoc work with microbial fuel cells. And it's interestingly, and I think in a Caribbean context more than almost anywhere else in the world, he developed the world's first solar-powered packaged wastewater treatment plant. He did that for the Canadian military for Algeria. And I know we've, I think in his, before Sentry was something that he had developed, he had done some feasibility studies and a bit of work in the Caribbean. And I think that's where he actually met Valerie.
No, actually, I brought him down to work in Castries on a wastewater project in St. Lucia. So he was staying in Rodney Bay, and we had a couple of his other guys were down there working together. So Patrick and I worked together for many years.
Yeah, no, that's awesome. And he's there's a picture of it in the office that I wish I was there. And so while he was developing this package treatment plant, he couldn't find a good way to monitor reliably. And there was the challenge of how does he support the operators there and monitor remotely, back from Canada, or will he have to send someone out there full time? And so rather than do that, he was able to support the operators remotely by developing the technology based on his postdoc work, and we'll dive into the technology. But as you can see, we've deployed around the world. Obviously, being Canadian, we're predominantly in Canada and the U.S. And then we've deployed across the world. So everything from the largest plants in the Americas in Sao Paulo, Brazil, down to parks in Canada, their latrines. So yeah, About 400 of these have been deployed globally, we detect about 27 events daily within the deployments we have, and that allows us to help clients who are operating treatment plants save money on a daily basis. And why is that? That's because we've developed a different technology to anything that anyone else has been using. So historically, when you want to monitor water quality, you're shining a light through it, or you have a membrane where you're looking for chemical reactions. And in, well, we'll call it wastewater, it's hard to shine a light through it. So you're constantly having fouling issues. And so fouling causes every other type of sensor to fail. But in the case of a bioelectrode sensor, which is the class that this is, biofouling actually powers the probe. So what does that mean? So we'll look at that in action. So at the end of the probe are two flat metal sheets. You're seeing a clean one on the right, and you're seeing two very, very dirty ones on the left. For anyone who's a football, soccer fan, depending on which term you use, those two probes are installed just south of Manchester United Stadium, and they were installed 18 months apart, and in a primary clarifier. So that's the other difference, is this probe was designed to want to be in wastewater, and so in that primary clarifier location, 18 months apart, never touched, obviously scientifically duct taped together. So that's not our recommended installation practice, but it is how it was done there. It's still, those two probes still haven't been cleaned, and they are still reading the same, or they're reading in parallel. And why is that? It's because at its heart, if you look at that's an expanded view of this tip right here. I'm just looking over to see that you can see through it. And so when we think about wastewater treatment, biofilm is consuming carbon. That's all it does for a living. And that powers all biological treatment processes. What we've done here is, if you look at the architecture and are familiar with microbial fuel cells, this is just a microbial fuel cell where, rather than trying to generate energy from it, we're counting that flow of electrons. So as the biofilm consumes carbon, it then deposits electrons onto our probe, and we count that, and that's how basic biological electrode sensors work. And so what happens is it ultimately is basically like a Fitbit for your plant's ability to treat the incoming wastewater. And so that becomes a very powerful tool, and we can talk about how it's being used and applied by a number of different groups globally. Again, what does a bioelectrode sensor measure? And so there's so many different ways to measure organics, COD, TOC, BOD5, CBOD5. What this is really measuring is, again, the consumable part of BOD, or in the case of a digester, those are the two main applications: influent variability monitoring and digester optimization. It's monitoring at what rate is the biofilm consuming food. And so it does compare very favorably to, a BOD5 lab sample. It's very similar to RBCOD. We've been tested against pretty much every type of organic metric, and where it differs from something like a BOD5 is if there's an industrial discharge that's toxic. The lab sample will be the same number, whether there's a toxic shock and an inhibitor or not. But a bioelectrode sensor will still pick up that the plant is less able to treat the incoming wastewater. So it becomes very powerful for real-time operations and decision-making, almost like a supplemental tool and a way of the biology telling the operators on site or remotely that there's an issue and that possibly a change needs to be made. Any questions? I'm happy to take a couple there, and then I can dive into how it's used. Hearing and seeing none. We'll keep going. So what does it actually look like? So this sensor takes a reading once a minute. And so a normal, happy, plant with no industrial discharges, no inflow and infiltration issues, it's going to have a nice diurnal trend. Kind of like how there's a flow diurnal trend, but, quality, it doesn't take a lot for an industrial discharger to mess up a plant. At our home plant, just near us, just near our headquarters in Prince Edward Island, there's a town of 3,000 people, and a microbrewery will throw off their treatment processes. So it doesn't take a lot to knock it off kilter. And this plant right here can very much look like this plant, and the flow is the same. The smell may even be pretty similar, but the outcomes are very different, and it causes the operators and the operations team to possibly get a bunch of flack for something that they may have not caused, because you don't always know what's coming into the plant. One of the fun things we've learned through monitoring around the world is there's one universal truth for almost every wastewater plant in the world. It's that if there's an industrial discharger in there, they will discharge at 4 o'clock on a Friday, and it hits the plant at between 5 and 6, and everything goes out of whack, and it messes up your dinner, depending on when you eat dinner. So how it's used. So there are 3 main places that we do that we've deployed these and seen how they've been effective. If there are a number of industrial dischargers that cause issues, you can put these in collection systems and pre-treatment sites and lift stations. They do need power, and they help identify much further in advance what's coming down the line. So this has been done in places like Phoenix. It's going into Salem, Oregon. Singapore PUB is probably the largest such deployment that I've seen of that, where it was at 6 industrial dischargers, 3 lift stations, and then at the headworks. And it's interesting to see how a big spike or toxic shock flows through and gets diluted out, but some of them don't, depending on the strength and or time of day. So what we're looking at here is, industrial dischargers just hammering with toxic shocks, cleanouts of tanks. It could be any sorts of chemicals, heavy metals, things like that. And then conversely, industrial discharges with organics. We are deployed downstream of a Red Bull plant, and it's very cool to see that Red Bull also gives the biology in the plant wings too. They love it. It supercharges their day. Most common use that we've seen is influent monitoring, headworks or primary clarifier, depending on the configuration of the type of plant. Mounted in a tank, mounted in a channel, and that's really the best place to monitor for any optimization or understanding of what's coming in, because essentially the clarifier headworks location, it's the extension of the collection system, but it's also the furthest forward point in the plant. Great question, Erwin. Sorry, I'm seeing that, so I'll throw the answer in right now. It will, so fog will have an effect on it. I can actually show you how fog is how fog interacts with it, or how fog additions interact with it with anaerobic digesters. It's when installing it, this type of sensor is great as long as it doesn't get bags or rags on it, or if there's odor control, ferric dosing. or in like hydraulic dead zones where fog can build up, because really they're designed to want to be in the flow, and then having the biofilm that's on the surface able to consume a representative flow. Hopefully that answered your question. And good one, keep them coming. So at an influent location, you can see a lot of different types of patterns and different issues. So high organic loadings, you can see that spike up. Industrial discharges that have some acute toxicity, you can see that coming down. And then dilution from rain events. In the standard operating procedures that have been developed by the engineers and folks we've collaborated with, the first question when there's a low signal is, to diagnose the issue is it raining? And then there's a series of cascading questions based on whether or not it's raining, and how to treat the incoming wastewater and potentially make changes. And our team, and I'm sure other teams at other groups are, developing machine learning tools to quickly identify what type of issue is coming down is being picked up by the sensor. And so there's a number of case studies that the groups have used. I'll dive into the Frankfurt one in a little bit, but Sewer Authority Mid-Coast side in California, that they're reducing their non-regulatory sampling by 80% because they just rely on this, sampling at 9 a.m. every day. You're going to pick up whatever was happening at 9 a.m. every day, and that may not pick up the things that cause plants issues. Peterborough, that was a fun one. They're actually just up the road for me. Their plant turned blue, which could be toxic. So their historical method of dealing with that was they'd ramp up aeration, they'd start sampling, they'd change some chemical dosing, but a couple of times we picked up that it was just food coloring from a food production facility, and so really food coloring has no impact on on treatment, so they were able to save quite a bit of cost and time. And then I'll dive into Frankfurt for anyone who likes Buffalo Trace. That's where they make that. They're also being tied into auto samplers. So this is an ISCO auto sampler, and then this is a Hawk auto sampler, because it's a challenge to sample when there's actually an issue. And that's historically been something where random sampling or composite samplings don't actually pick up, the acute issues that are happening and when they're happening, to trace them back to the folks who are sending them down in our catchments. So the other most common use is digester monitoring. So looking at digester health. So first off, looking to prevent any souring events, because downtime and souring and reseeding it costs too much money. And the others are then to optimize biogas. So this type of sensor is very useful because it's a leading indicator of biogas production, because it's essentially monitoring that consumption of VFA, which allows for a very good understanding of that biomass health and can it take in the organics that are currently being discharged to it. And so what that looks like in digester monitoring is, this is what happened when a system was restarted. So rather than having to load, test, wait for 3 days for a VFA analysis, load, test, wait, it can be done in more real time. And this was done in agricultural digesters, actually 2 in Ontario and then 1 in BC to understand how its effect. The other interesting point is that because it's a leading indicator of biogas production, it's great. So as you're driving more and more organics loaded into the digester, those two signals will match. And it's when they diverge, when the biogas production plateaus and the signal for organic loading still goes up, that's the maximum loading that can be done within a digester. And so then it's all about setting the risk tolerances, 10, 20%, whatever the tolerance for the specific plant is, to a point where it can be monitored and optimize that renewable energy. And it's also been used to prevent digester souring events and pick those up earlier than other types of tools. So in short, when looking at a real-time signal over the course of days, ideally life is good. It's in a good band, but the second that organics start to ramp up within a digester, it's start taking corrective actions at a certain point, and then immediate actions if it gets to a certain high point, or if toxicity gets in, it's taking countermeasures to prevent that from destroying the biomass health. Any questions before I jump into 2 case studies and how plants like yourselves are using this?
You mentioned about some of the I probably missed that in terms of the fluctuation in near real time monitoring of signals. Do you have some of these challenges in terms of your fluctuations in real time data with the signals, as it were?
Great question. So the fluctuations, so it'll pick up whatever food is available to it. So what we have seen is, if we're right near a pump, we'll see the pump cycles, the pumps turning on and off. If we're on a recirculation line, we'll see that, because the bugs just want food, and it's the same as how your plant will operate. They'll just want that food. When we have compared it with a UV vis that was right next to it, the UV vis was a bit smoother. I think there's some corrective algorithms going on there, whereas this is very much a raw signal, so it's going to be a little bit more sensitive, and it's been trialed in everything from drinking water, where it's sensitive to fluctuations there. I think it was San Jose in a drinking water reservoir, where obviously on the y-axis here, it's in the hundreds. In drinking water, it was in the decimal places, and so it is sensitive to exactly what the conditions are at that time, and will react basically as fast as the biology will react when eating. Did that answer? Great question, by the way.
Yeah, thanks. Yeah, that's good.
Perfect. So let's dive into Frankfort, Kentucky first, and then CMSA. So Frankfort, Kentucky, not Frankfurt, Germany. When I present this to Germans, they love that. It's home to Buffalo Trace, which is one of the world's largest bourbon distilleries. Obviously, I love the rum down in the Caribbean. So this plant, they've got 14 industrial dischargers. Trace is the biggest. They discharge 150 meters or yards from the inlet of the plant. And it's a town of about 30,000 people. They do have other dischargers, but really just one massive one. And so what happened for them was, and this was about 2 years before we started working with them, they had or 2 months before we started working with them, they had a plant kill. So Trace discharged something. They didn't or forgot to. There's varying stories on why the plant wasn't informed. But the plant manager walked in and could already smell and see that his plant was killed. And so for 2.5 weeks, they were in violation. So he talked to a partner of ours, and the rationale for looking at BES was the reliability and real-time monitoring to optimize their sampling, identify their loading trends, and then they wanted to fine-tune some process decisions as well. And what this helped them do was the ability to see what was coming down from the distillery. So a little spike here from a discharge, fine. A big organic overload there, that's indicative of something that would actually cause them quite a bit of issue. And this plant suffers quite a bit from rain dilution. Though it is funny because they also suffer from snow melt. Probably not an issue for anyone here. But there was one time where we early on when we were deployed with them in the spring where we called them up and said, is it raining at this plant? And the comment was, no, it's warmer and all the snow is melting. They also in the first week or the first month of working with them had a big issue every Wednesday at noon. And the reason that they were having a big issue every Wednesday at noon was because they were taking in landfill leachate at one of their lift stations, and the collection systems team wasn't talking with the plant team, and so no one knew that. They were also cleaning out their EQ tank at the same time, so they were basically double hitting themselves, and they couldn't figure out that they didn't know what was happening or why they were having these issues until they were able to sit down and have that conversation with the whole team and say, what's happening at 12 o'clock? So they shifted the landfill leachate receiving to a different time, and that enabled them to smooth out and not have to spend more energy and consumables on treating it effectively. And so they installed these basically at their headworks, where they have their industrial line and their municipal line coming in, and at their splitter box. So now when they see an organic overload or a toxic shock from the landfill leachate that is above a certain threshold or below a certain threshold, they divert to their EQ tanks so that they can deal with it later. And that's one of the more straightforward ways of dealing with an issue and applying this type of technology to that. Seeing a question. Great question. So it's the parameter for biomass health is it's consumable BOD or consumable VFA. They correlate quite well to the traditional CODs, TOCs, BODs, where when they're toxicants or other things that are coming into play, the correlation may not be as exact, but this is a very much holistic and reliable type of technology. So it's not a specific parameter. It's much more of a rate based of how much biomass can be consumed by the plant at any given time. And we can dive into that. I've got some slides with correlations on them in the appendix if we want to dive into that deeper. Great question. All right, so so typical uses, they will divert, they'll change their blower speeds and their oxidation ditch, they'll dose different chemicals. And with this plant found, and there's Carl, their plant superintendent, looking at the dashboard. They found that they were able to manage their oxidation ditch more effectively, and they're in the process of looking into feed forward aeration control to further optimize that, and they're saving about $100,000 a year through using this tool. And they're also looking to put one right at the outflow of some of their larger dischargers like Buffalo Trace. I'll hop into any questions on that, or I can hop into a case study on co-digestion and the use in AD. Hearing none. Great. So Central Marin Sanitation Agency, that's based in California near San Francisco. So they, the plant as a whole began operations in 1985. They've got, 2 1 MGD mesophilic digesters, and they have a strategic power delivery program. So their entire goal when they upgraded to co-digestion a few years ago was how can they produce, one, be self-sufficient in terms of production of energy, and 2, sell excess energy onto the grid. California has, has had issues historically with brownouts and lack of reliable energy. So this was another way to just continue to add energy to the grid, and provide a source of extra income for the municipal treatment plant. It's no secret that every treatment plant in the world could use more money, and so they're able to use that to supplement their cost of operations and then improve their plant more, or at least that was their goal. And we'll get to the point where they are able to do that. So we've been working with them for 4.5 years now. They have a pretty straightforward process of that they take organics and take and truck them into the digester. And the first key to that is you want to safeguard the process. Adding food waste, fog to digesters, that can go wrong pretty quickly. And with using 3-day VFA, the challenge is, can you operate something real time while waiting for 3 days? And so that we started working with them and collaborating to see if this could help, understand the load test wait approach. And so in the first phase, it was identify if these sensors could be used to protect biomass health, and then see if it could help monitor organic loading in real time. And then the second phase was to use the sensors to monitor that loading in real time and to begin to load more organics. So we're through, and the state of where we are is we're past phase 2 and we're moving into phase 3 to understand if digesters can possibly be loaded beyond the 50% more loaded that they've been able to achieve through real-time monitoring. And so in the first phase, they put 2 probes on the 2 pilot digesters. Pilot digesters are much safer to play around with than the real ones. They were deliberately trying to overload and sour the digester with organic loading. And what you're seeing here are the 2 digesters, loading, consuming all the food overnight, loading again, and the bioelectrode sensor picked up 3 days in advance of VFA that something was off. Looking back, it likely would have been earlier, because even though the peaks remain the same and then those start going up, if you look, the troughs are trending upwards. And so what it's saying is that the plant is, and the biomass is struggling to recover, and is starting to take on issues. And so this one was fed all the way through just to confirm. And you can see that they went pretty off. But that gave the confidence that this type of technology could be used to help monitor that. And we're naturally conservative because we have to be with digesters and wastewater treatment in general. But digesters, if you get it wrong, there's so many issues that you can have that it's not worth getting it wrong. And so typically, digesters are loaded 30% less than they could be because of that risk tolerance. So the next phase after, and so it was basically to move to phase 2, it was assessing the loading strategy, developing custom operating procedures for that site, to really maintain biogas production. So sensors were able to proactively identify stability, and then, again, show that they could, at the very least, protect against digester failure and downtime. And then, as they were moved to the full-scale digesters, it was the goal to increase organic loading to divert organic waste from landfills, and ultimately generate biogas. So, it's almost a double win of, being able to get paid tipping fees for taking in the truckloads of organic waste, and then also generating excess electricity. So what was very cool was that you could see differences in loading and in a number of ways. So what you're looking at, April, May, and June of 2021, you're seeing, this is the normal fog and food slurry edition. They were doing some maintenance, so they stopped taking anything in. And what you see here is this is actually the baseline of just the organics from the wastewater treatment plant. And so you could see a good baseline, happy, healthy, normal diurnal trend. If that was all that was coming in, you'd never have much variability. But again, the goal was to increase organics addition to generate more biogas. So they started doing it again, and with just the food slurry at first, to start getting a good baseline of, how can we ensure that we're starting this up effectively. Then this is a more granular look. They started to load fog again, and you can see that the fog, frankly, the biology and the biomass within there likes to eat fog. It's much more active, and to take that one step further, they started loading one fog load a day for every 3 days, or one fog load every 3 days, and then they began to take in one truck of fog per day, and that allowed them to have that trust to push through. So we're a few years on, and now what they're able to say is that they've been loading 30 to 50% more organics for a year, and that's producing quite a bit more renewable power that they can export. So the green line is the renewable power used, and the purple is the power that they're able to export. So the majority of their power is coming from these digesters, and it's allowing them to sell back onto the grid. So the ultimate outcome was, phase one, cost of downtime imbalance, $100,000 able to protect. In phase two, and in work with conjunction with Stanford University, able to increase organic loading 30 to 50%, which led to a doubling of biogas production and about $600,000 in additional energy, either through not having to buy energy or selling it onto the grid. So any questions there? Those are the two case studies. Happy to chat about those. A few slides left, and then we can take more questions. Seeing none. So they're easy to install. I've installed them before, and anyone will tell you that that means it's pretty easy. It plugs into a wall outlet, so standard North American plug. The second that happens, the universal SIM card starts sending information to the cloud, and you're able to see that data live in real time. The most typical installations are either tank or channel mount, or threaded into a pipe. I've installed them in 35-40 minutes, which again is a pretty that speaks to how easy they are to use. A standard system comes with two sensors, because that way you can look at the beginning and end of a process and see how the treatment performed. It goes back to the roots of wanting to monitor a package treatment plant at the influent and see how that performed at the effluent when it was out in the desert in Algeria, and being able to monitor that back in Canada. So you get quite a good wingspan in terms of 150 feet in any direction with cable lengths. Like I said, installation's a breeze. And cleaning is the key thing. Like I said earlier, this type of sensor wants to be in wastewater. If, however, you get something metallic lodged between the two electrodes, the easiest way to clean it is squirt water between the two electrodes and get that out of there. Otherwise, we send toothpicks, a box of toothpicks with the inside the panel, which, if we forget to tell people that, it leads to a bunch of questions as to why are you sending me toothpicks at a wastewater plant. Yeah, it's being used in quite a few applications. Aeration optimization. We're doing some feed-forward aeration optimization with a few partners. Nutrient management, effluent monitoring, auto sampling, industrial discharges, and starting to develop more on the machine learning and AI insights and reporting with ourselves and partners. Yeah, I mean, this is just a quick, I'll skip over that, but essentially it's when this is deployed, it's deployed with the equipment, but also training online through smart people like Iker, who's on the call. And they essentially act as an always-on person to support your operations team in making decisions, because there's 6 or 7 people on our team who all day, every day think about this signal. And so it's every treatment plant is unique, but the problems that treatment plants face happen quite often across the world. So there are some really smart people that work in this type of field that are able to that folks that we collaborate with are able to call on at any given time. So that's about it. I mean, the goal is to know early so you can act. And happy to take some questions, and thank you for having me.
Right, thank you, John. This is highly technical session, but I think we had a few good contributions with people like some of our wastewater people on board, such as Mr. Gill, has some good questions in the chat.
Yeah.
So now the floor is open for questions from some of you who probably just joined. You may have missed some of the earlier parts, but feel free to probe John with any questions you have now.
So maybe I'll ask a question to everyone here.
Definitely, Simon.
So, what types of issues are common that you face at a wastewater plant? I mean, it's what are the industrial dischargers that cause issues? What keeps you up at night?
I think Mr. Gill says, could you review the application in an activated sludge plant?
Sure, and I think Iker will can help me on this. So it's really the question is can the plant handle the incoming organic load? And when I go like this, that's my motion for the bugs eating the organics, and that's the most challenging question. We try and figure that out with respirometry, pH monitoring, temperature, flow, things like that. But those are all in real time, trying to get at the question of, is there an issue coming down the pipeline? And so the biofilm that's in the activated sludge process is going to take over and be the same biofilm that's on this type of sensor. Oh, how about settling? I know we have dealt with settling issues. Iker might know actually more, and if you can either shake his head or I can go for it. We have had some. Our goal is to be in free flowing. So if there is not to be in the settled part of the tanks or channels, and we've had some times where when primary, depending on how primary clarifier is operated, that at the inlet and outlet you'll see very different organics, and that's usually based on the solids or organic loading based on the solids settling. Hopefully that's answering your question. If not, I can get you a better answer from someone smarter than me.
Also, I think there was another question. I don't know if we had already dealt with that one about what parameters do you use to determine the biomass health? I think you dealt with fogging.
Yeah. It's a great question because it's every other parameter is a very absolute parameter, whereas this is a rate-based parameter. So it's the rate at which organics are being consumed by the biology in the plant. So it does compare, and I can pull up a slide. I'll just share this. The short answer is the parameter compare. So we listed as consumable BOD. The closest parameter that it would correspond to is either VFA or RBCOD, because it's essentially what is consumable by the biofilm in the plant or the biology at that point in the process, and at what rate is it going to be consumed. So looking at these, the 69% we were stationed right next to a TOC analyzer. This was at Southeast Water in Melbourne, Australia. Hopefully the West Indies beats them in cricket in the World Cup. And what we were able to determine was this probe corresponded very well to TOC and actually had a better correlation to the TOC lab samples than the TOC analyzer, and the TOC analyzer was being maintained once a week, calibrated once a month, whereas this the recommended maintenance is quarterly visual inspections after the first 3 months, where it's monthly visual inspections for the first 3 months. And this was this was part of a presentation that Southeast Water gave at Ozwater. The COD, again, compared very favorably. VFA is the parameter that we correlate to the best, and that's because at that point in the process, there shouldn't be toxic shocks or anything that would affect the biomass in any way if the processes are working well. Again, this is in the States where it was compared against primary effluent BOD. The challenge, with every type of monitoring parameter is what is it being compared to? How is it sampled? How is this done? And so we've been run against ammonia sensors where we don't detect ammonia, but we detect the potential that there will be an ammonia breakthrough if there's a toxic shock. I'm presenting with the folks at Jacobs in a couple of months. They were running tests with FFBOD. So there's a million ways to measure organics, and this compares favorably with them. Did that answer the question? I went a bit more in depth. I can show you the longer question, or the longer deployment here, where You can see the screen grab of the two sensors moving in lockstep after they were deployed. That was the one that I was discussing early in the presentation. Oh, cool. Baker was writing. Using non-GL levels in a bioreactor.
Yeah, I think Ita has also responded to a question in the chat which asked, could you review the application in activated sludge? And he says, for organic loading detection and trends, figure out if there is high loads of organics or toxic materials on its way to the basins. Yeah.
So yeah, it was basically what Jan explained. Just put it in words.
Right. You have well had some quite a bit on, well, I guess traditional treatment plants, mechanical treatment plants. Would that mechanism work in the case of some of the nature-based systems, such as a constructed wetland? So of course, we'd have to do the effluent testing before the water is released into natural environment.
Great question. We've done we've done some lagoons at pulp and paper facilities. The short answer is yes, we could do it. It's robust and reliable. We've had them outside in northern Canadian pulp and paper lagoons, and we monitor a couple of lakes in Florida that are used for recreation. The question would be what changes could be made based on the signal, whether it's loading alterations or anything like that. So I'd be happy to discuss that and whether we would actually be a right fit for the economics of that circumstance. Okay. And we're pretty open and honest. If we don't think it's going to work, we're happy to say no and try and recommend a better solution. Just seeing Daryl's question, and I can answer that. Can it be used to monitor DO levels in a bioreactor? That's a great question. So in terms of the signal, so the signal times flow, given a factor of a time factor for the residency time, is the direct leading indicator of the oxygen demand based on the wastewater quality. So we did some work with Black and Veatch. They're leading wastewater experts based out of Houston and Columbus, Ohio, and developed different protocols to help understand what the DO requirements would be. And so that's basically the process that we're using in a few feed-forward aeration controls.
Right. Any other questions, colleagues? I think this was another one of our very good productions, and I would like to thank Jon and Ika for joining us this afternoon and sharing with us some of their expertise and their technology that is being applied in other places and which may well be useful in some of our jurisdictions. As it is, not many of our jurisdictions you find these types of massive treatment facilities. So I think it is a work in progress as some utilities seek to upgrade their facilities. And of course, sharing with us the knowledge with our operators certainly helps with our education process and helping to improve our infrastructure in the Caribbean region. And as you quite rightly said, I think in your last slides, that to monitor effectively, you would need to know early so you can act And that is, I think, useful in almost every aspect of water and wastewater utility systems management. So we'd like to thank you immensely, and like to thank Valerie for making the contact with Sentry. And we look forward again in the near future that we may be able to continue such collaboration.
Yeah,
So,
it's interesting, Ignatius, because we started off this season with Jerry Hanna, I think, where he was talking about a very simplistic wastewater lagoons and pond system. And here at the other end, you've got the larger monitoring systems. So we're going from very simple to something that is simple but complex.
yeah.
And then next week we have Dave Holland and Neil Van Dyne coming from Haiti. So we're going to be talking about their non-revenue water, but they'll also, I think, be able to give you a good update on what is happening in their area in Haiti. So it'll be a very interesting presentation from the region.
Right. Thank you for that. So colleagues, thanks again for joining us. If it's Wednesday, it's CAWASA webinar, and we discuss from A to Z with respect to water and wastewater systems. Have a good one, everyone, and it was a pleasure having you on board. I'm Ignatius John, the Executive Director of CAWASA, signing off. Have a good evening all. Bye.
Thank you
Bye,
very much.
everybody. Thanks, John.
Thank you so much. Have a good one.
Thank you.